Alright, so this is kind of the last video directly related to electron configurations, and we're going to look at some exceptions to the electron configuration rules that we've been learning. So there are a number of reasons why we might have exceptions to the electron configuration rules that we've been learning. The one that I want you to be aware of is when we have orbital subshells that are either completely filled or are exactly half filled. These are especially stable electron configurations. So 3D5, where the D subshell is exactly half filled, or 3D10, where the D subshell is completely filled, or 4p3 and 4p6. Atoms really like it if they can have these as part of their electron configurations. And so there are other reasons why we might see exceptions, especially when we get up to the really high energy orbitals. They get really close together, and so we see a lot of weird things and exceptions happening. The only exceptions I'm going to ask you to be aware of are for copper and chromium. And they are exceptions because of exactly this factor, that half-filled and completely filled subshells are particularly stable. Right? And I'm not going to ask you to know these exceptions, but you can imagine, right, when we start getting up into occupying orbitals that are in this region, the orbital energies are so close together that there may be many reasons why they might adopt different configurations. And so when you see the electron configurations for particularly like the inner transition metals, and they're kind of all jumping around, it's because oftentimes they can lower their energy by putting electrons in different subshells, allowing them to get further apart. And so moving into a slightly higher energy orbital might be offset by the fact that the electrons can get further away. And we know because all electrons are negatively charged, they don't particularly like being near each other. Alright, now if we look at copper, so copper is right here. And so if we were going to write the electron configuration for copper, we might predict that it is, right, so let me write them in. We've got the 1s, the 2s, 2p, 3s, 3p, 4s, and then copper's filling the 3ds. So we might expect the electron configuration for copper to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d9. But it turns out this is not the electron configuration for copper. And so what happens is if I take one of these electrons from the 4s subshell and I promote it into the 3d subshell, I can end up with a 3d10 and a 4s1, where I went from having a completely filled subshell and one that's neither half filled nor completely filled to, so the actual electron configuration for copper is and so the reason copper adopts this electron configuration, so it's the same number of electrons in each case, but I've taken one of the 4s electrons and put it into the 3d orbital, and now I have a 4s subshell that is exactly half filled and a 3d subshell that is completely filled. Right, so both of these are favorable. I've got a half filled and a completely filled, whereas previously the 4s2 was completely filled, but the 3d9, that wasn't particularly stable. So by promoting an electron from the 4s to the 3d orbital, copper can get a particularly stable electron configuration, and so it does. And so you'll want to remember copper as being an exception to the electron configuration rules. And this is one of the two exceptions that I'm going to ask you to remember. And the reason I ask you to remember these exceptions, even though there are a lot of other ones, and I don't want you to have to try to memorize all of the exceptions, I think it's important to remember at least a couple of them to highlight the fact that the half-filled and completely filled electron configurations are particularly stable, and to remember that there are in fact exceptions. Alright, so one more. If we did chromium, we'll see a similar thing happens. So chromium is right here. And so we might expect the electron configuration to be and just like copper, the Ds are sort of one away from being particularly stable. And so they'll do the same thing that copper does. It'll take one of the S electrons and promote it into that D subshell. And so the actual electron configuration for chromium is and therefore the all of the early subshells are completely filled, and then the last two are exactly half filled. And so chromium is willing to pay that energy penalty to promote that S electron into the Ds so that all of the subshells are either exactly half filled or completely filled. And then this is just to sort of show you, especially when we get into the inner transition metals, right? The resolution here isn't great, but you can see there are all kinds of exceptions when we get down in this region. And so I won't ask you to remember these guys, but this is largely in part because the energies of these 5F and 6D and 7S orbitals are all really close in energy.